and we have a Lagrangian filling L, then there is a certain number, so it's called TB, Thurston-Banach number, and this number is basically some sign times Euler characteristic of the filling. So what does it mean? It means in particular that if we consider dimension 3, right? And in dimension 3, we consider, let's say, Legendrian links or Legendrian nodes, then the topology of the node is basically completely described by this formula, because we will have this Euler characteristic of basically a punctured surface, right? And punctured oriented surface is determined by its genus. So from this perspective, it makes sense to speak about the types of fillings that may exist. And recently there was a question of existence of infinitely many diffeomorphic and so-called not Hamiltonian isotopic exact Lagrangian fillings. Usually these fillings and the general Lagrangians in symplectic geometry and topology are considered up to Hamiltonian isotopy. So these questions of existence of infinitely many diffeomorphic and not Hamiltonian isotopic exact Lagrangian fillings for Legendrian submanifolds received certain amount of attention, in particular because of the formula on the top. And then in 2020 and 2021, there were a series of papers. So the first result is due to Casals and Gao that answers this question positively. And later there were results of Van Bailey, Casals, Zaslov, Gao, Shenwen, and they developed some basically shift theoretic clusters type of, and also holomorphic methods to detect this infinitely big family of exact Lagrangian fillings. In fact, the paper of Casals and Gao, as far as I know, just got accepted to Annals. So, so these results are really new. So what we will do today, today we would like to discuss some extension of this principle and some extension of these examples to high dimensions. So there will be two results that I would like to present. So the result number one basically says that if you have the big enough dimension and you consider the standard contact vector space, then in this standard contact vector space of high enough dimension, we can find the product of spheres, which has infinitely many exact Lagrangian fillings distant up to Hamiltonian isotopy. And the second result is that if you consider just connected Legendrian submanifolds, then we can find the basically Legendrian submanifolds with a collection of fillings, such that this collection is, so this family is infinite, and besides that, it can be split into subfamilies, each of which consists of diffeomorphic but not Hamiltonian isotopic fillings, and each two families are not homeomorphic to each other. Okay, so we have basically this infinite family, and it can be split into non-homeomorphic parts. Okay, so this was a motivation and my results. Let me get to some preliminaries or whatever, some definitions, because so far maybe for some people it looks like general words, you know, without seeing the proper definitions. So once again, what's a contact manifold? So contact manifold is an odd dimensional manifold, which is equipped with a maximally non-integrable hyperplane field. Usually it's denoted by Xi. And this Xi is, so even though it sounds a bit difficult, but this Xi is basically given as a kernel of potentially local one form alpha with the properties that alpha which d alpha to the nth power, which power is different from 0. And this Xi is usually called the contact structure, and alpha is a contact form which defines it. Then as far as the fix one form, and as a matter of fact, this form is not unique, because if we have one Xi, we have one form alpha, we multiply it on the nowhere vanishing function, we will get another contact form, right? So as far as we fix a contact form, but not a contact structure, then we can define so-called the Reeve vector field. So this Reeve vector field is uniquely determined by two conditions. So the first condition says that the evaluation of our contact form on this vector field is equal to 1. And also, and the second condition says that if you take inner product of this vector field with d alpha, then we get 0. So the first condition basically says that this vector field is everywhere transverse to the contact structure, because contact structure is a kernel of our one form. And the second condition says that basically the flow of Riemann vector field preserves contact structure. Now there is a typical example, and we will mostly play with that. So the example is we have a standard Euclidean vector space, contact vector space, namely r to the 2n plus 1 with the standard coordinates x sub 1, y sub 1, blah, 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 x sub n, y sub n, and z. And we have a one form which is a dz minus sum of yi dxi. So whenever we consider the kernel of this one form, that's a standard contact structure. Now, why do we play with just standard contact vector space? One can ask, well, one can consider a more general contact manifold. The point is that in contact geometry, there is a Darboux theorem, which basically says that every contact manifold locally looks like a r to the 2n plus 1 with this given contact structure. So from this perspective, whatever can be shown for the standard contact vector space also works for other contact manifolds. Okay, now let's talk about Legendrian submanifold. So Legendrian submanifold of r to the 2n plus 1 is basically n-dimensional submanifold, which is everywhere tangent to the contact structure. And as far as we fix our Legendrian submanifold and we fix a contact form which defines a Riemann vector field, we can speak about so-called Riemann chords. These are trajectories of integral trajectories of Riemann vector field which start and end at a given Legendrian. One can, so we also give some notation. So Q of lambda will mean the set of Riemann chords of the Legendrian submanifold lambda. And one can ask questions about the properties of this Q lambda. What can be said about it? Can it be finite? Can it be infinite? So we will today we'll consider only closed Legendrian submanifolds. Namely, we'll consider manifolds with compact manifolds without boundary. And for this Legendrian submanifolds, this Q lambda is generically finite. So namely, you can have it infinite, but with a small deformation of Legendrian, with a small Legendrian isotopy, if you wish transformation, one parametric transformations through Legendrians, you can always make the set finite. Besides that, one can ask about like how big the set is. So is it empty? Is it non-empty? It turns out that this guy is non-empty. And this is basically a conclusion of the old Gromov theorem, which says that basically in the standard symplectic manifold in Cn, one cannot have an embedded exact Lagrangians. So they should always have at least double points, and these double points a priori will correspond to these reports. Okay, and one can ask once again the questions about the size, and typically this type of questions can be seen as a part of the Arnold conjecture, or type of Arnold conjecture. Now, what type of tools we will use for our feelings? What type of tools we will use for the proof of our theorem? So the tool that we will use will be so-called relative symplectic field theory, or so one of its version, which is called Legendrian contact homology differential graded algebra. So what is this algebra? Is basically a tensor algebra. Let's say over field. This field could be Z2. Let's say for simplicity, which is freely generated by this Q lambda. So once again, we know that Q lambda is generically finite, but since it's a tensor algebra, namely it's non-commutative, it's huge. There is a certain gradient. This gradient is coming from the Maslov index, or Conley-Zender index. And I will not talk about that, but there is a differential. So the differential is interesting. So how to define it? So let's say we have a Riemann chords C+, C1 minus, and Ck minus. And we would like to define the differential D on C+. So what is it? It is basically given as a word C1 minus Ck minus times some number. And what is this number? So in order to define this number, we do the following. So we basically consider disks, let's say standard unit disk in C. We consider standard unit disk in C. We remove some points from the boundary. Okay. So let's say we remove point X and Y1, Yk. on C, we have a standard complex structure. And then we consider R times R to the 2n plus 1, namely so-called symplectization of our contact manifold with a symplectic form D times D of e to the S standard contact structure, where S is a direction on the first R factor. And on this product, we have an almost complex structure that we denote by capital J. This almost complex structure should satisfy some properties. In particular, it should map contact structure to itself. D of alpha VJV should be greater than 0 for every V in the contact structure. And it should also be R invariant. And by R here, we mean the first R factor. And besides that, it should map DDS to DDZ. Okay, and we consider the moduli space of such punctured holomorphic curves, namely maps that satisfy Cauchy-Riemann equation with respect to I and J. Inside R times R to the 2n plus 1, with the property that the boundary of this disk lives on the Lagrangian cylinder over Legendrian, so namely on R times lambda. And these boundary punctures are asymptotic to these ripcords. So one boundary puncture is asymptotic to C plus, and possibly many boundary punctures are asymptotic to C1 minus CK minus. Okay, so we consider this modular space of pseudo-holomorphic punctured disks. And if you're lucky, this type of object has a geometric structure, namely it has a structure of manifold, let's say. And here, as you see, we count the number of elements in this modular space up to the translation, so up to some R action. So what is this R action? This R action is basically the translation in this S direction. Namely, if you wish on R times R to the 2n plus 1, it's a translation on the first R factor. Okay, so if you have one-dimensional guy, we take a quotient, we get a zero-dimensional guy, then Gromov compactness theorem tells us that we have a compact zero-dimensional manifold, and we can count the number of elements there, because basically we are counting the points. Okay, so that's a Legendrian contact homology DGA, or if you wish, some version of the relative symplectic field theory defined by Eliashberg, Giventhal, and Hofer. And it's a nice thing in a sense that it provides invariance up to Legendrian isotopy. So whenever we deform our Legendrian through one parametric family of Legendrians, then basically the homology of this algebra will survive. The homology of this algebra will provide us an invariant, algebraic invariant. Now, let me say that here we are dealing with the coefficients in F, or for simplicity, one can say Z2, but sometimes it's better to use more sophisticated coefficients. In particular, we can take coefficients in group rings over H1 of lambda, or group ring over, let's say, Z over pi1 of lambda. And sometimes we can use Novikov coefficients, so one can do many things. Now, there is a notion of exact Lagrangian cobordism that later corresponds also to feelings that we already discussed. So basically, exact Lagrangian cobordisms, they provide some functoriality in this theory, namely the existence of such guy will lead to the map between these differential graded algebras, right? And how do we define exact Lagrangian cobordism? Basically, if we have two Legendrian submanifolds, lambda minus and lambda plus inside the standard contact vector space, then we say that lambda minus is exact Lagrangian cobordant to lambda plus. If we can find the cobordism L with a negative end lambda minus, positive end lambda plus, an exact Lagrangian embedding into this symplectization, right? Namely R times R to the 2n plus 1 with the symplectic form D of, okay, on the previous slide it was S for the direction, for the first R direction, here it's T, sorry about that. So D of e to the T alpha standard, so T is a coordinate on the first R factor. And basically these Lagrangians, they are cylindrical over Legendrian's lambda. So whenever this first R factor So whenever we have some minus infinity to some minus t, let's say on the first R factor, so whenever we get to closer to negative infinity and closer to positive infinity, we have a cylindricity over lambda plus. So what happens in the middle is compact. And besides that, so once again, we would like to have something exact. So what does it mean? It means that there is a function on our Lagrangian. So this function is small f with a property that d of it is a primitive of our symplectic form, right? And it's strange, but somehow in this theory, in order to be able to compose these cobordisms, one needs to assume that this function restricted to this cylindrical ends must be constant. A priori, it's just locally constant, but it turns out that if one does not make these assumptions, then there will be some problems with the gluing of such cobordisms. And if you have a exact Lagrangian cobordism with an empty negative end, then we will have this exact Lagrangian filling, okay, that we already discussed. And if we have Legendrian which admits several exact Lagrangian fillings up to Hamiltonian isotopy, so in the different Hamiltonian isotopy classes, then the Legendrian is called polyfillable. So now, if, as I said, so this exact Lagrangian cobordisms, they provide some factoriality for this Legendrian contact homology DGAs. There was a work of Honda and Kalman, which basically shows that if there is exact Lagrangian cobordism, then there is a DGA map from the positive end to the negative end, from A lambda plus to A lambda minus. And in particular, if lambda minus is empty, then this leads to the DGA homomorphism that we call augmentation, and is basically a map from the Chicano-Feller, or from the Legendrian contact homology differential graded algebra of lambda plus to the ground ring. Because if you don't have anything, so if lambda minus is empty, then, and we know that this algebra must be unital, we still, we at least need to add the, we at least need to have the ground ring there. So we have this map epsilon L, and it's a map from A lambda plus from the algebra, which corresponds to lambda plus to the ground ring with zero differential. So this map is once again a unital DGA map. Okay, this type of map is called augmentation, and it turns out that these augmentations are right tools in order to extract information from this relative symplectic field theory DGA or Legendrian contact homology DGA. So they allow to linearize it. And the linearizations, so the first person who actually discussed these linearizations was Yuri Chikhanov. Okay, so so this map that I mentioned on the previous slide, right? So it was abstract. Now, how it works concretely? Once again, so since we know, so how it works concretely, since we know that there is this exact Lagrangian filling L, what we can do, we can define this augmentation by basically counting the holomorphic disks with only one positive puncture at the rib chord. Okay, so this is basically the picture of what we can see in this particular situation. Now, yeah, now let me say the following. So what we will do today and how we construct this type of examples, basically we use some version of suspension that exists in contact geometry. So in the simplest version of it, so-called the Swan Suspension, was defined by Ekholm, Etnayer, and Sullivan long time ago. And then it was extended to a more sophisticated types of suspensions that can be also extendable from the Legendrian submanifolds to the fillets. Okay, so the type of suspension we will use is called the spherical spinning or from spherical spinning. So let me talk about that. So what is this spherical spinning? So let's say if you have a closed orientable Legendrian submanifold and we have some particular embedding of it. So in order to define this suspension, we need to have not just a submanifold, but we need to fix the particular embedding. So we have this particular embedding. This embedding is given by f lambda. So we can write it in coordinates x1p, y1p, blah, blah, xnp, ynp, and zp. Then we can always assume that the first x coordinate is greater than 0. Why? Because our contact form is dz minus sum of yi dxi. So basically, there is no x factor in this contact form. So whenever we do shift in the x direction, we don't change anything. So this will be a legitimate Legendrian isotopy. And since we have a compact Legendrian submanifold, we can always shift it in one of the x directions and nothing bad happens, right? So from this perspective, we can assume that one of the coordinates is greater than 0. And what we can do, we can define this suspension. So this suspension will be defined in terms of its xz projection, okay? So we basically take xz projection defined by f lambda. We add some extra coordinates, namely x tilde minus m plus 1, blah, blah, x1 tilde. And we use them in order to consider as x1 as basically a radius of a sphere, and we add some extra angular coordinates in order to define the spherical parameterization. So this way, from the old parameterization of lambda plus this extra part, we can get something which can be seen as an xz projection of the Legendrian submanifold of type lambda times Sm. Okay, so we have this type of guy. This guy is singular. So a priori, what we do with the xz projection and this type of procedure done by this capital phi is singular, but we can lift it to r to the 2n plus m plus 1, and we get a Legendrian submanifold in r to the 2n plus m plus 1, which topologically looks like lambda times Sm. Okay, so this is a version of suspension. So in this form, at some point, I did it, so it appeared in my paper. So it turns out that this type of specifications, this type of construction naturally extends to the exact Lagrangian Corporatisms, namely one can do the spinning, and if you have a Legendrian with a exact Lagrangian fill-in, we can spin it together with this fill-in, so you get a spun Legendrian with a spun fill-in. Okay, so basically that's a picture of what happens. So let's say what you see is a standard, is an xz projection of the standard Legendrian unknot, or if you wish, first on Bannekin -1 unknot, and then we do S1 spinning here. Okay, so we just add one extra coordinate and we do the rotation. So we get a torus. Okay, so from this definition, once again, we see that this suspension is diffeomorphic to Sm times lambda. And as I said, so we can extend this guy to the fill-ins. So there are also some other versions of this construction. So one can do more sophisticated stuff. One can actually twist it by the elements of, let's say, for S1 spinning, for elements of pi1 of S1. And here we can also we can do the twisting by the Legendrian isotopy. Here we use a simpler version because somehow we will have to deal with the algebra, this relative symplectic field theory algebra. And for that, more sophisticated versions do not provide us the right answer. Okay, so we will deal just with this simpler version of spinning. Now, we will need some fact that was basically proven by Holm, Honda, and Kalman for simple coefficients, namely in the case of field coefficients, and by Cecilia Carlson in the case of more sophisticated coefficients. And it says the following. So if let's say we have a spin exact Lagrangian fill-in of closed Legendrian with Maslov number 0, then our or Maslov plus 0, then L induces, so our fill-in induces an augmentation. So we already know that, which to the group ring. So group ring not over H1 of lambda, not over the first homology group of the Legendrian, but to the group. So we have a group ring over the H1 of L, namely we have a first homology group of the Lagrangian. And this first homology group, this group ring lives entirely in the gradient 0. And besides that, if you have two exact Lagrangian fill-ins that are isotopic through exact Lagrangian fill-ins, then there is a DGA homotopy between corresponding augmentations that correspond to these fields. So probably it makes sense also to mention that in the case of the standard contact vector space, being exact Lagrangian, being isotopic through exact Lagrangian fields is the same thing as being a Hamiltonian isotopic. So these two things are the same in the case of the standard contact vector space. So we will use this type of statement, and we need to apply our suspension to some examples, and the examples that we will take were discovered by Casals and N. So basically there is a family of links. I will not describe it, so there is no like a very good description of those, but I will just mention some node types that appears there. So in particular, we have a node type 10-139, mirror of 10-145, mirror of 10-152, 10-154, and mirror of 10-161. So this class in particular contains this type of links. So here you can see this XZ projections of the links, where this n-1 and n-4 basically correspond to the n-1 and n-4 full twists. Okay, so these are the families. So these families are basically the guys for which in dimension 3 we have these families, infinite families of exact Lagrangian fields that are diffeomorphic but not Hamiltonian isotopic. And we need to mention that all these guys, so in these families described by Casals and then all these guys, they have Maslov number 0, all Legendrians, and basically all chords have non-negative degrees. So in these settings, the useful observation is that two DGA maps from our Legendrian contact homology differential graded algebra to the ground ring are DGA homotopic if and only if they are equal, and that's a positive part. So somehow, in order to do the distinguishing, in order to do the separation of the fields, we can just separate the augmentations, these linearizations of the relative SFT or Legendrian contact homology differential graded algebra. Okay, so from this perspective, if you would like to show that two fields produce augmentations to the ground ring that are distant under all isomorphisms identifying H1 of L and H1 of L primes, then we can say that L and L primes are not Hamiltonian isotopic. So that's the way to go. How do we prove theorem A? So just a strategy. So we take Legendrian, which was considered by Casals and N, so this family. We take two exact Lagrangian fields, let's say L and then L primes that are diffeomorphic and not Hamiltonian isotopic. We do the spinning as we mentioned. And what we need to show, so we know that basically this type of construction extends to the field, so it's fine. And we need to show that whatever we get are not Hamiltonian isotopic exact Lagrangian fields. Okay, so that's a key thing that we need to get. And using the observations that we had on the previous slide, what does it mean? It basically means that we need to show that the augmentations coming from this spans of the fields, they satisfy this formula that basically for two of those, they cannot be related by the composition with a certain automorphism of our DGA or certain automorphism even of the ground ring, which basically makes them the same. Okay, so we have this formula that you can see here. So once again, so Hamiltonian. Okay, so two fields. If you have two fields that are Hamiltonian isotopic, then basically this formula holds. So in order to show that it doesn't hold, we need to show that in order to show that they are not Hamiltonian isotopic, we need to show that this formula doesn't hold for any phi. Okay, and if we assume that they are Hamiltonian isotopic and we have this type of formula, then we would like to reduce it basically to the formula for the original fields, so that if it works, we know that they are Hamiltonian isotopic, and this way we will get a contradiction, right? So once again, we take two exact Lagrangian fields. We know that they are originally not Hamiltonian isotopic. We take their spans. So let's assume that they are Hamiltonian isotopic, then we will have this formula. And if we can show that this formula reduces to the formula about the original exact Lagrangian fields, then we will get a contradiction and we are done. Okay, so how to get something like that? So how to follow this strategy? So now one needs to analyze how the this Legendrian contact homology differential graded algebra behaves. So whenever we take a span, so something happens with the fields. So basically, we do not have something happens with the chords. We do not have. So basically, we have families of chords. We do not have isolated chords, and these families of chords, they form so-called Morse-Bot family, and so the set of chords of the span of lambda, using some Morse perturbation, can be actually perturbed into the chords that correspond to the north and south pole of the sphere with which we do this, with respect to which we do this type of suspension. So once again, this span is topologically just a product of the original Legendrian and the sphere, and we know that rib chords, they also form the spheres, and then what happens, we need to do some perturbation in order to split these chords into the parts that correspond to the north pole and south pole. Okay, so the part that corresponds to the south pole, namely this QS, can be identified with the original rib chords of lambda, with this Q lambda, and this type of identification, it preserves the index of the chords, or the gradient of the chords. And there is also a canonical bijection between the chords that corresponds to the north pole and the original chords on lambda. But in this case, we do increase the gradient by the dimension of the sphere. So if you do the spinning with the SK sphere, then basically we increase the gradient by K. And in this case, so with Yorgos Dimitriglou-Rizal, at some point we show that basically this Legendrian contact homology differential graded algebra of lambda is basically a subalgebra. It's just a subalgebra of the algebra of the suspension of the span. And besides that, this inclusion map, this I, can be left inverted. So there is a map pi from the Legendrian contact homology DGA of span to the Legendrian contact homology DGA of the original Legendrian, which is a quotient map. And this quotient map, so if you compose it with I, it gives us the identity map. Okay. So we did this type of computations with Yorgos in the case of the simplest ring, ground ring, namely for the field. Namely, we do it for Z2. Now one needs to do some extension procedures, so one needs to play with basically this group rings, but it's possible to do it, and we do it. And this type of correspondence, so this type of maps, I and pi, they leads us to the maps between the augmentations of our Legendrian submanifolds lambda and the span of lambda. So basically this way we can find a bijection between augmentations, and we can see how the augmentation on the span looks like if it comes from the augmentation of the original Legendrian. So there is this formula relating epsilon and epsilon tilde. Right. So now, so a priori, we do not know. So we know that we can get this type of augmentations, so this type of induced map, but we do not know that whether whatever we have for the span Legendrian, whether this type of guy is actually geometric, whether it comes from the field. So we just know that existence of a field leads us to this type of map, but a priori, it's not true that every such map is geometric. Maybe it comes from the field. So one needs to show that basically whatever we get as this epsilon tilde is a geometric map, namely it comes from the field. And this field in particular is this is a span field. So that's what we do. And so if it happens this way, then we can really do the reduction. So this way the proof works. Of course, the meat of this proof is this one-to-one correspondence between augmentations. And basically this fact that whenever we do consider this augmentation of the span, then it's actually geometric, that it comes from the span of the film. Yeah, so that's the end of the proof of theorem A, which was about one infinite family of diffeomorphic but not Hamiltonian isotopic guys. So whenever we take two exact Lagrangian filaments that are not Hamiltonian isotopic, we take their spans, they will not be Hamiltonian isotopic, because if they are, then basically they we have a okay. Then they will lead to the conditions that epsilon L composed with phi is equal to epsilon L primes, and this will contradict the fact that the original ones were not Hamiltonian isotopic. Okay, so now in order to get to theorem B, we need to consider some other family of Legendrians. This is a family of Legendrians constructed by Tsao, Golub, Haydn, and Sablov. So I will start with the two-dimensional guys. So how to get them? You basically take the links that are described on the picture. So they can be obtained from several copies of a trefoil that are slightly moved to each other using some Legendrian Reidemeister moves. And then what we do, so we have this type of picture, then we perform the S1 spinning to this type of picture, and then we do attach handles along the red lines that you see on the picture. So if you just take a link, you do S1 spinning, you will get something not connected, but whenever you attach handles, you will get a connected guy, okay? So this way, we can get surfaces, Legendrian surfaces, and Tsao, Golub, Haydn, and Sablov showed that this type of surfaces, they have a, so depending on the number of components in this link, they can have arbitrary finite number of non-homeomorphic filaments for these surfaces. So if they are non-homeomorphic, in particular, they are not Hamiltonian isotopic. Okay, and then we can always leave the dimension by doing the suspensions that we have discussed. Okay. Then why the connectedness is important? So in this case for theorem B, you will get connected guys. So here it's a more sophisticated version of the formula that I already mentioned. So if you have in dimensions 3, basically if you have a Legendrian link and it's a boundary of some Stein surface, living in the boundary of Stein surface, okay, in the boundary of Stein surface, and in this Stein surface we have exact Lagrangian filling, then basically Thurston-Banach number of our Legendrian is equal to the minus Euler characteristic of this exact Lagrangian filling. Okay, and in particular, if you know that our lambda is connected, namely it's a knot, then the topology of it is completely, the topology of the filling is completely determined by this Thurston-Banach number. So here we will get examples, once again connected examples, but we will have families that are split into non-homeomorphic parts. So this will be the consequence, whatever, this will be the result of theorem B. So how to get it? Once again, we have these examples of Sablov and company, and we have the examples that we get in theorem A. So what we do, we would like to perform so-called zero surgery, ambient zero surgery. So it's a procedure that was described by Yorgos Dimitriglou-Rizal, and basically in high dimensions. So if you would like to, if you don't want to see the definition, in high dimensions, it's simply a version of a connected sum operation. So if you have two guys, they are separated, let's say by some x coordinate, we can perform this surgery and we will get something connected, okay? So basically it's a picture of what happens in dimension 2. So for Legendrian submanifolds in dimension 2, we can have this singularities. As you can see, it's like a cusp times interval, and that's here you can see how to perform the this connected sum operation or ambient zero surgery operation in terms of this type of singularities. So the basic idea of proof will be to take our lambda. Once again, our lambda is a Legendrian coming from the theorem A, and we have X. So these guys are these spans of the examples coming from the Sublof and family, Sublof and company, and we perform this type of zero surgery operation. So this zero surgery operation, as it turns out, it leads to the exact Lagrangian cobordism with negative end lambda and x, negative end lambda and x, and with a positive end lambda pound x. And then we can glue the filaments for lambda and the filaments for x. So this way we will get something that in general, so that for which we can show, or we can try to show that, you know, we have this, so this type of glued guys actually gives us the family, this infinite family. It turns out that this zero surgery or ambient zero surgery construction provides an injective map between the augmentations of the negative end to the augmentations of the positive end, and using the fact that this L-axis, so this type of filaments, they can be separated by the topology, and L-lambdas can be separated by the Hamiltonian isotopy. We see that, yeah. So we see that basically we have this family. So the infiniteness will be given by the infiniteness of the family L lambda. So the separation by the homeomorphic, so into the non-homeomorphic classes will be given by Lx. And basically the way to separate them using augmentations will come from the fact that every augmentation of the positive end, namely of lambda pound x, can be, so its DGA homotopy class can be actually reduced to the DGA homotopy class of our lambda, and the topology gives us the rest. So that's basically what, like, that's all what I would like to present today. Thanks a lot for your attention.